Hello, welcome to video 23 in the lecture Advanced Mathematic Modeling. So in the last videos we I introduced stochastic processes. We have seen how to characterize stochastic processes, and we have seen the most simple or trivial example of independent, identically distributed random numbers where we don't have memory in the system. And now the thing is, how can we generate other more interesting stochastic processes which have some memory and some more interesting properties which we can use to model something in the real world. And this will be the random walks. So random walks will be the fundamental notion or process how we generate more interesting stochastic processes. So, and maybe I just start with a simple example to get the main idea. Example, let's say we have a repeated Bernoulli trial. So we have random numbers EI. So I is the time index, and there will be just either, now we call them -1 or +1. That's the two outcomes that are possible, and this should be independent, identically distributed random numbers, so IID process. And so from this process we can visualize this in form of a time series. So here we have our time index I. We have 1, 2, 3, 4, 5, 6, 7, and so on. Here we have the EI, and then at every time here we have +1, -1, and then at every time point we have this Bernoulli trial, so it's either +, -1. So for example, in this case we have +1. The next time step we have again +1, then we draw -1. So we're always independent random numbers. We have again +1, minus, and so on. So that would be our stochastic process. But this process obviously is a bit too boring or something to describe a real process. But now think, how do we, when we model, let's say we want to model something, model a system. So we have, the system is characterized by a state x at a certain time point I. So that's what we're interested in. We want to have a state of a system which depends on time. And then very often in modeling, and this is also already when I start my first modeling 1 for undergraduates, so we write down that the typical assumption is that the model describes the change of our state variable from time point I to the next time point, and then we write here as the sum of all processes that are happening. So the state in the future is the old state plus the increments. I call this, write this here. So the new state equals old state plus the increments. And so the increments, they contain all the information of the processes birth rates, death rates, or whatever chemical reactions and so on that's happening to our state. And this equation just makes a balance to see how these processes change the value of the state. Okay. And now, so this ansatz you can also use when you have a deterministic system, but now we're in a stochastic world, and now we just say the processes happening on our system are described by our stochastic process. So this increments these numbers is given by a realization of our stochastic process. And this motivates then to look what's happening if we then sum these values here and say what's happening if we define the state at the next time step as the old state plus the increment. So let's make a plot of x. So this can be positive, negative. We have again our time axis. We have here the position xi. And let's say we need an initial value. We start with x at position 0, which is now arbitrary. So, and then what is x at time point 1? It's x0, this is x0 plus the increment at time 0, so we need also an increment at time 0. Let's assume here the increment was also positive, so that we can better see it. So I colored the increments in blue. And then the next time step, now we need here our time steps. Then at time step 1, our state has evolved to 1. Okay. So what's happening at time step 2? x2 equals x1 plus the increment 1. Increment 1 is 1, x1 is 1, so in the next time step our state equals 2. So what is our state at time step 3? It's 2 plus again 1. We are here. But now in the next time step, it's time step 4, our state is 3 minus 1, and then we go down again. And then in the next time step we go up again, and we go down again, and we go down again. So in fact our state, and let's assume maybe here we would have another positive value here to make this a little bit larger, then our state would increase again. And so you see from our process that we generate, in this construction we generate a new process which describes the state of our system. And this process, which is defined in such a way where the increments are given by a stochastic process, we call this a random walk. And why walk? Walk comes from the association that we say that's the position of a particle, and the change of the particle depends always, the increments tell us what is the changing velocity basically of this particle. So in for 3 times the changing is up, so the particle moves upwards, 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 then we go 1 down, then we go 1 up, down, down, and again up. Yeah. So that's so like we say that's a random walk, so the walk of a particle up and down on this axis here as a function of time. In this way, so we obtain the like a walk position in time, position of object in time, or you could say we obtain here a profile, so like we get a certain characteristic function, or we obtain a profile. So sometimes, and since this walk is random, yeah, because like the shape of the profile depends on the realization of this process, that's why it's called a random walk. No? And now random walks you can do also for more interest, for other stochastic processes. Here it was the most simple. The increments are just from -1 and 1, and we have independent random numbers. But of course you could now take an arbitrary stochastic process, interpret this process as increments of a random walk, then just do this procedure, and then we generate a profile out of this. So we generate a random walk. So the random walk is defined. It's a new stochastic process. So the xi are a new stochastic process which is kind of generated from the stochastic processes of the EI. Sometimes people take this more literally, or and then we say X, that's the position of a drunken man. So this man leaves his pub, which is here. He's totally drunken, so he cannot control his movement, and then he goes either left or right, totally random. And then by chance, sometimes we will go a little bit in one direction, then by chance sometimes we will go eventually another direction. And then you can ask if his home is maybe at position 7, how long does it take him to reach home, for example. Yeah, so it's a drunken man's walk. Yeah. What you have to take in mind is that the profile that we find here eventually depends, of course, on the realization of our stochastic process. So if we would take another realization, we would throw again random numbers from our Bernoulli trial. This would look a bit different, and then also the random walk will look a little bit different that we obtain from this. And already by eye, it's clear that this profile here, this looks already more like something which we can use to describe some real process in the world than this just up and down thing here. So by this way, integrating or summing over stochastic processes, we see already we generate some profile which has some interesting properties. Now this things becomes really interesting if we go a little bit further than just 7 time steps. So let's see how this looks if we generate a large number of such time steps. So first, what's our increments are doing? Maybe if you know longer time step. So here I have made a plot how this could look. If we have the increments, which is either just 1 or -1, and yeah, so this plot looks boring. So like this should be a time series where we have now very small, so it's very compressed. So then we have this very small space between the next points. So we have maybe here, I don't know, 50 realizations, and the points just jump between +1 and -1. Sometimes you have a strike that for a certain time you have always 1 and -1. Sometimes it's iterating often. But when you look at this, so you don't have much information when you look at such a realization. And for example, if you see such random numbers, then there's a question, are these really independent random numbers? Maybe is there memory or not? And just by looking at this, you will not see so much. You will see basically the histogram of the increments. So you see, okay, we have always +/-1. You see we have some change. Your eye might identify such strikes of where you have always for a long time only one number, which happens by chance. But if there's a memory something, it's very hard to see. Now when you take these random numbers and construct the corresponding random walk, so here's index I. Now we plot the x, and so then the random walk looks typically a bit more interesting. It has some, could be something like this here. So it's a rough profile. You see fluctuation, it might go up or down here, and then you see, like for in the mathematics, random walks are sometimes a process which is generated to learn something about something else. So before I said the motivation for the random walk construction was that we want to model the change of a state variable. Yeah, that's also true. But you could also say, okay, that's just a formal construction to generate from the increments another random walk, another stochastic process, because the x, of course, are also a stochastic process, which allows us more insights into these random numbers. And now what would happen if we take a different realization of these random numbers? We would have again here twiggling between plus and minus 1. There. It would look by eye the same, but the typical random walk might look very different. There. If you take another realization, this time the random walk might look something like this. Maybe the second one I do in blue. And then you make another one, then it might be like this. And you take another one, it might look like this. Yeah. So it's clear, so that so we have here different realizations. And if we have here different realizations in the independent IID stochastic process, we don't see that much difference, but in the random walk we already see much differences. Yeah, so that's already starting to be interesting. So now this was here a stochastic process where the increments were taken from a certain distribution. So let's say, so the increments they're first taken from a certain distribution. And here, for example, we had this Bernoulli trial P of E was either +1 or -1. So we had this distribution where we just had these two possibilities which each have 1/2. Of course, you could have something else. For example, we could have a distribution where the increments taken from a uniform distribution, from a continuous distribution. So the increments can also be taken from a continuous distribution. You can still make the same construction, but if the e's are continuous, it means that the jumps from one time to the next are not of the same length, but sometimes you make a large jump, sometimes a small jump, whatever. But it's still a random walk. It's still discrete in time, but the increments can be really realistic. So you could have, for example, here uniform distribution. We could have, for example, a Gaussian distribution. Then the question is now, depending on the distribution of the increments, what are the properties of the random walk. But maybe we don't have the distribution. Maybe we have have given the moments of the increment. So from the increments we don't have the distribution, but we know the moments, etc. So maybe we know the mean value, which in this case is 0. Maybe we know something about the standard deviation, or the second moment. Maybe we know something about the covariance, outer covariance. We know something like this, so we know some moments of our increments, and then we would like to calculate the properties of our new random variable of the x. So the fundamental problem, or the fundamental question given the properties of the increments which could be the probability of our increments, maybe as a function of time if it's not independent random numbers, if it's not identical random numbers, so the probability will change in time, or it could be given in form of our moments, in other moments here. Given these property, given this, then the question is determine the properties of the random walk. So that's the fundamental question, of course, that we want to address. And so we want basically to know what's the distribution of the position of the walker. Can we say at a certain time here? So it means, are we able to tell at a certain time point that we choose here? We take here a certain time axis at this time. Can we say something about this distribution that we obtain here for different realization? Where will the walker be? What's the mean position of the walker? Yeah. And when I see so here I say the distribution, but when I say what's the mean position, so I could also be interested what's the mean position of the walker. I could also ask, so what's the standard deviation? Yeah. So we want to know something about or the variance. So how large is this distribution here? Or can we say something, like about memories in the walker and so on and so forth? Yeah, these are things that we would like to know. And so in the moment, so our process it's determined. So we have our definition how to create a random walk. I gave you the main task that we want to look for, but maybe I should give you some more motivation why this is so interesting. And so let's maybe look at some examples. So where do we find such profiles, and where could they play a role? So let's look a bit at examples. And so, for example, one typical example where you see always such curves that would be the stock market. Yeah. So then you have the stock over time, which tells you something about the state of your economy. And again, you see the change in the shares or in the stock. So like what's really making everything is the change in the stock. So like the stock is just at a new time, at the next day is the old stock plus the change, and the change. So the increments contain all the information about the economic processes or the financial processes. And what we see here is just the random walk, the sum over the increments, which determine if so the stocks are sum over the financial processes. And then typically you have these functions, and if you know something about the properties of the resulting random walk, you can make a lot of money. And here, for example, in stock markets, people are interested to make some predictions. So if we know the time until here, we are at this point, and then we would like to know is maybe was there an increase? Did our economy increase? Did we have a trend in the system or not? And then we would like to anticipate, will it continue like this? Or maybe we might get a crash and stocks go down, so we want to have some predictions, and so on and so forth. So if you know properties of the this random process, you can make a lot of money. Another example, that's very actual, very current, it's climate change, where we also see such graphs, and this would be, for example, temperature, either global temperature or temperature of the environment in a certain time frame. Here you see these things, and again, the temperature at a certain time point here, or the temperature at a certain time depends on the temperature before plus the changes, and the changes are where all the climate physics is in there. So the state at the next time point is the state at the old time point plus the increments. We have again here, this is the basic equation, and this means here, so that's the temperature, and this epsilon, the increments and the climate change. The increments, that's the processes, that's the heating, warming, or whatever of the atmosphere. So that's the climate change, the climate processes. And so here in climate change, we are then interested, if we have such a curve, we want to know, is this increasing or not? We see a lot of fluctuations there, but do we see a trend? Is our climate warming up or not? That's the question we want to know. So, and of climate models, for example, they predict here the energy fluxes and losses in the atmosphere, and then we sum up, and then we get our temperature profile. So what would be other examples? I mean, that could be also, if we were speaking about money, this could be your bank account. So, and then the state of your bank account in the next day depends on your old bank account plus the money you earn minus the losses when you buy something. You have the same, basically the same thing. Or you could have population dynamics in ecology. That's your abundance of the species you're interested, and the change or the abundance at a certain time depends on the processes, and that are your birth, death rates, immigration processes, and so on. We have time series like this. We will, let me see, you could have here a chemical concentration. here, again changing in time, or maybe nowadays when we have epidemic, so that could be here the number of your corona cases. And then the number of corona cases in the next day depends on the corona cases before, then plus the incidence, the new infected people. So that's why in corona very often you see the increments nowadays, and there are all these newspapers and so on where you see how many, what's the incidence in the last day, so how many people became infected, and then of course you have also to subtract how many people are recovered. This data you usually don't see. And then you can calculate the number of infected, the number of corona cases in as a function of time. And there also we are interested, how does this profile look? Is this exponentially increasing? Is it decaying again? We have this, maybe we have waves, so a lot of time, long time, maybe we had small prevalence, and then suddenly we had an outbreak and so on. Yeah, so and when you see, like, if you think about typical problems, topics that people are interested, that are in the news every day and that are very important for society or future, like climate change, the stock market, the whole economy, here epidemics or pandemics. So you see, a lot of this can be boiled down to this concept of random walk. That's why this is so fundamental. And then maybe, this video is getting long, but maybe let me do one last thing. We can also have random walks in higher dimensions. So for example, random walk in 2D. And this means then our increments are a multivariate from a multivariate distribution. So we have our increments, they're vectors. So there we have an x component and a y component. So we have a vector of the increments, and then we write down the same, and then our state is a vector. And then we say the state in the next time point is the state before plus the increment. Now we have a vector sum. Yeah. So it's everything transforms straightforward from the 1D random walk to a 2D random walk. Now let's take a simple example. Let's say we have increments which can be, here's x and y direction, so the increments can be only +1 in x, minus 1 in x direction, +1 in y, or -1 in y. So we have only 4 possible increments here. So going to one step left, right, or up, down. And then we have our vector x. We start at 0, and then now we can go, for example, one step to the right, then maybe we go one step up, maybe we go one step left, maybe we go right again, then we go up, we go right, we go down, maybe right, down, left, and so on. And then maybe we, in this way, we construct a random walk. Yeah. And the random walk can repeat, can come again on position as it was before. It's the same in 1D. In 1D also we can, the position can come to a point where it has been before. This happens also in 2D here. So on this we can interpret now as the trajectory of a particle or an animal. And again, so this is how it looks when you have a small number of time steps, and when you have a large number of time steps, and you get your trajectories which look maybe something like this. Yeah. And this 2D random walks are used when we really want to model the movement of particles or animals. And I will come to this also. So 2D random walks have really the physical interpretation of movement. For example, all movement ecology roots in 2D random walks. And the 1D random walk, this movement analogy is just in the name, but typically we don't model a real movement in 1D, but this X then is rather interpreted as something like here stock market, climate, temperature, and so on, bank accounts, and such state variables. So sorry this video was a bit long, I forgot to break it into parts, but so I wanted to introduce you to the random walk as a fundamental notion to create new stochastic processes. And so in the next video we will see how we can calculate properties of the random walk. For now, thank you.